So hello, in this video I'm going to address the quantum mechanical tunneling effect. Quantum mechanical tunneling. So what actually is the problem description or the agenda? We are interested in the behavior of a particle that hits a potential barrier, and we are interested in the probability that this particle can pass this potential barrier. So for clarification, we draw here the situation. We draw an x-axis, and on this x-axis we have a potential barrier indicated here in red with a height v0, and here let the position x equals 0, and here the position is x equals to L. And with this coordinates we can define three different regions. So the first region is that x is lower than 0. The second region is that x is between 0 and L, and the third region is x is greater than L. And in quantum mechanical tunneling, or in the problem we are interested, a particle comes in from the left side and hits the potential barrier. And since in quantum mechanics this particle can also be described as a wave, what we expect is that some part of the wave will be back reflected. Some part of the wave will transmit here into the potential barrier, and at the end of the potential barrier there will be back reflection and transmission. And we give now each of these waves a symbol, or let's say describe it with a letter. Here this incoming wave should be, let it be psi1, the second wave here is psi2, the back reflected one. Here it's psi3, psi4, and psi5. And the value we are interested in is the transmission coefficient. So it's actually the part of the incoming wave, or the ratio of the probability density of the incoming wave in relation to the outgoing wave. So the transmission coefficient t therefore can be defined as the ratio of the probability density function of psi5 divided by the probability density function of psi1. And as you already know from quantum mechanics, so this expression here describes the probability density. And for completeness, here also in region 1 the potential is 0. In the mid region the potential is constant, having value v0, and here in the third region potential is 0 again. So as usual in quantum mechanics, for getting the value of t, we first have to write down the Schrödinger equation. So it's minus h bar squared over 2m, then psi double prime it's a function of x plus potential v, which in our case is described by these three regions here above. So it could also be dependent on x. In our case, within the regions, it is not. Then the wave function again. This equals E, the energy, times psi of x again. So this is the stationary Schrödinger equation. So the third thing I would like to do is reduce this second order differential equation, the Schrödinger equation, to two linear first order differential equations. Therefore, I define phi equals psi prime. And if I plug this into the original Schrödinger equation, then I get minus h bar squared over 2m phi prime equals E minus V times psi. And these two equations can also be written in matrix vector notation. So this gives us, first we write the differential operator, then a vector psi and phi, and this equals, here again, vector psi and phi, 0, 1. Write this expression again here. And here it's also 0. And for simplicity, I define that A is this matrix here. The next step is that I choose an ansatz for this psi phi vector. It is psi phi vector equals to some unspecified constant Cn times some now unspecified vector Vn, and e to the power of lambda m n times x. So if I plug this ansatz into this matrix vector notation above, I get lambda n, because here on the left side we have to take the derivative of this vector ansatz, which is lambda m times Cn Vn vector e to the power of lambda n times x equals a c n, so this vector ansatz again, Vn e to the power of lambda n times x. And essentially this reduces to the equation a times this unspecified vector Vn equals lambda n times Vn vector. So this is now an, as you may already know or may know from some other lectures, that this is an eigenvalue problem. So we can rearrange this equation if we first multiply the left side with the identity matrix, A times Vn vector equals the identity matrix with essentially changes nothing here, times lambda n times Vn vector. Therefore we can bring the right side to the left. We arrive at a Vn vector. Oh, sorry. Then we arrive a minus lambda n times I times Vn vector equals the 0 vector. And as you will see, this only makes sense if we make the assumption that Vn is not the 0 vector. So we are not interested in this case. This would be the trivial case. We are interested in finding actually vectors for Vn that are non-zero and corresponding values for lambda, which are the eigenvalues, and these are the eigenvectors. And one condition that has to be fulfilled such that this expression here becomes 0 and Vn is not a 0 vector is that the determinant of A minus lambda n times I equals 0. And we can write out this expression. We know A from above. So this is the A matrix. And the diagonal elements are now in this expression minus lambda n. So write it down here, minus lambda n. 1 v minus e to m over h bar squared. Here it's also minus lambda n. So we can calculate this determinant. It's lambda n square minus v minus e to m over h bar squared. And this polynomial here has two solutions. Let's call them lambda 1 would be the positive square root of v minus e to m over h bar squared, and lambda 2 equals same expression, just negative value in front. Now, we have now calculated the two eigenvalues of this eigenvalue problem. Now, the next thing we have to calculate are the corresponding eigenvectors. Therefore, we, for example, take this lambda 1, plug it into this equation star here, plug it into this equation, and then see what the components of Vn has to be such that this equation is fulfilled. So we can do it here. We calculate the eigenvector corresponding to the eigenvalue lambda 1. So we say here, it's write down lambda 1 here. So now let's complete this matrix expression here. So from this it follows that v1 vector has to be the positive square root of this expression here from above, and the lower entry is 1. So similarly, one can find v2, which is the negative vector, a vector with the first entry being negative. The lower entry is 1. So we have now found the two eigenvectors and eigenvalues corresponding to this eigenvalue problem here. And this eigenvalue problem came from an ansatz that we plugged into the two differential equation we actually want to solve. So now therefore we can write down the general form of this psi phi vector, which is essentially a linear combination of the two eigenvectors we have found, or we have made an ansatz. It turned out in this ansatz we wrote down some unspecified vector. Turned out that this vector is an eigenvector that solves the problem we are interested in, and because we have found two eigenvectors, a linear combination of the two possible ansatz types containing the two different eigenvectors will generally be a solution of this vector here. So therefore we can write down C1, some unspecified contact, v1 vector, e to the power lambda 1x plus c2, v2 vector, e to the power of lambda 2x. So actually, as you remember, this, as I already said, this comes from our ansatz. And our ansatz yielded in two different eigenvectors, and these two eigenvectors, they are linearly independent, and therefore generally one can write this psi phi vector as such a linear combination containing these two linearly independent vectors. Now the question is, why did we do this? Now we are in a position to write down general versions of this psi phi vector for the different regions we have defined in the beginning. So in region 1, lambda 1 and lambda 2 are complex. This is because in this region potential is 0. Therefore, if you look here at this expression, if v is 0, then this expression in the square root is negative, and therefore lambda is complex. So for this purpose, let's define a equals the square root of 2me times divided by h bar squared. And here in this region, lambda 1 equals I times A, and lambda 2 equals minus I times A. And the general form of the psi phi vector in this region is now defined as this expression. So again, here I write C1, but it's not the same value as here. This is just the general version of this psi phi vector, but here now it's psi phi specifically defined for region 1. But again, hopefully this doesn't cause any confusion. Here I use the same expression as here above. Whatever this yields minus IA 1 e to the power minus IAX plus C2 IA 1 e to the power IAX. So now in region 2, V equals V naught, and we have set the condition then that V naught is greater than E. So E again is the energy of the particle we want to investigate. But however, now this leads to the fact that lambda 1 and lambda 2 are real. And for this purpose, let's define B, just for the reason of simplicity. It's V naught minus E times 2m over h bar squared. And as you see, this expression is real. The value under the square root is positive. So therefore, let's define that psi 2 and phi 2 are C3 minus B 1 e to the power of minus bx plus C4 B1 and 1 are the entries of this vector, and e to the power of b times x. And in region 3, lambda 1 and lambda 2 are complex again, like in region 1. So here we pretty much get the same result, or similar result as for region 1, just I give the constants in front of the eigenvectors different numbers. Let's make this here C5 minus A1 x plus C6 IA 1 . So now before we proceed, let's ask for the physical meaning of these terms here. We said initially we were interested in the problem that some particle wave hits a potential barrier and the particle wave comes from the left side. And the question is, can we now identify some expressions here as left-going and right-going waves? And the answer is yes. One way to do is that we have a look at some physical reasoning or some physical reasoning actually, yes. Or better say some physical meaning. And for this purpose, just rewrite again the first component of the psi phi vector corresponding to region 1. So psi in region 1 is generally psi1 minus ia e to the power minus iax plus c2 ia e to the power iax. And that's defined now big phi of x equals c2 ia e to the power of iax. And calculate the expectation value for the momentum of big phi. Therefore, we have to apply the momentum operator to the wave function in such a way that we calculate the following integral. So this brackets here, they indicate that we are calculating an expectation value. And big phi star means the complex conjugate of big phi. Here again, the complex conjugate. And now we write, as known from quantum mechanics, the momentum operator. This now gives same value below the bar, or same expression. H bar times A. As you see, if you apply this operator to this function here, then you get the value h bar times A and the original wave function again. And this equals h bar times A, which is bigger than 0. And this means that the wave that is described by big phi travels to the right because the momentum value is bigger than 0. Correspondingly, this expression here, C1 times minus ia times e to the power of minus iax corresponds to the left-going wave in the original diagram. So therefore, follows that x describes wave traveling in plus x direction. So this is important because here in region 3 we can already see, because of how the problem is set up, that C6 should be 0. sorry, C5 should be 0. And after having clarified this physical meaning, we can also state our transmission coefficient again, because now T would be, as originally defined, we said this is this value from the first slide, but again, due to our analysis, we can say that it must be actually C5 times minus IA minus IAX squared over C2. This is now C5 over C2 and its corresponding probability density. So next step would be to apply boundary conditions. As usual for waves, we say at an interface that the wave itself and its first derivative with respect to x have to be equal. So in our vector notation, since we already said that phi equals psi prime, we can write our boundary conditions as follows. Psi 1, phi 1 at point 0 equals psi 2, and at L the same must be true. The wave function in region 2 at point D and its first derivative, which we have defined as phi. So these are our boundary conditions, and if we write them down in terms of the expressions we have derived before, we arrive at an equation system. First equation, second one is, or first vector equation, and second vector equation now. So here we have two vector equations with vectors having two entries. So this means we have 4 equations but 5 unknowns. But this is not a real problem. Sorry, here I made a mistake. Here I should read C6 over C2. Sorry for this mistake. Yeah. So therefore, let's divide simply both equations by C6 and define new constants, namely D I is defined as Ci over C6, and with this definition we arrive at the following system of vector equations. And this system of vector equations now has 4 unknowns and 4 equations. And we can rewrite this in matrix vector form as follows. So, very well. We are now at the point where we have done all the mathematical framework that allows us the calculation of a transmission coefficient. Because the transmission coefficient, as defined, equals the probability density of the ratio of the two coefficients that appear in the system of equations. It is namely C6 over C2, and that is nothing else than one over D2 and its probability density. And the calculation of this value will be carried out in the next video, as well as the interpretation of the result.